In this video, I'm going to talk about double integrals in polar coordinates. Now, in 15.1 and 15.2, we talked about double integrals over a rectangular region and general regions using Cartesian coordinates. Now, there's going to be regions where it's going to be much simpler to integrate using polar coordinates. So I'm going to skip a few of these slides because it's basically, you can read the book in 15.3, and the way they go about explaining how they come about doing the double iterated integral is basically analogous to the rectangular double integral. So suppose that we want to evaluate, let me get my pen here. Alright, so suppose we want to evaluate double integral over a rectangular region so now we got f, which is a function of x, y, dA, whereas the regions shown in figure 1. So you see these figures here are going to be difficult to evaluate. In either case, the description of R in terms of the rectangular is rather complicated, but R is easily described using polar coordinates. So we're going to do this through polar coordinates. Let's go to the next slide. Again, you know, you've got your R squared equaling x squared plus y squared, and R equaling R cosine theta, and y is R sine theta. So these regions, these circular regions, these disks, are really considered polar rectangles. So you can think of these in the polar coordinate system as rectangles defined that way. And your R is going to be the R theta, right? And R goes from A to B, and thetas go from alpha to beta. So here, the circle with radius 1, right, goes from 0 to 1, and theta is just obviously going to go from 0 to 2 pi. In this particular region here, we've got a circle with radius 1 and a circle with radius 4, but we're just looking at that kind of half washer. So we're going from 1 to 2 and to 0 to pi. All right. Again, I'm going to skip a couple of these things. We're really just looking again at these smaller rectangles. As it gets smaller and smaller, we're adding up all those areas. And again, we take double integral and we can change it to a polar coordinate iterated integral. So it's not fxy, you know, you got your x equaling to r cosine theta and your y equaling to r sine theta. R dr d theta is going to be your dA. The book states this, and I'm going to state this. Make sure you are putting in that extra r here. Okay, this is going to give you your area, and I think, yeah. So this is going to be your equation. Your r is going to go from A to B, and your thetas from alpha to beta. And again, they're iterating that. Be careful not to forget the additional factor r on the right in the side formula. So you can think of this rectangular, this polar rectangle, as having a side dr, d theta, and another side dr. So your dA, right, your dA is r dr d theta. Alright, going directly to an example. So we're going to evaluate the double integral over that rectangular rectangular region, 3x plus 4y squared dA, where r is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Alright, so again, we got that half washer region that they're talking about here. We're describing this region, right, as your y is going to be positive, right? It's above the y-axis. And your circle or your washer is basically between 1 and 4. They consider it a half ring. And the polar coordinates is given by 1 to 2 for your r. Alright, so your r is extending from 1 to 2. And your theta is from 0 all the way to pi. So now we're taking that r from 1 to 2, like we said, and theta from 0 to pi. The x is r cosine theta, so we're just doing substitution here, and your y is r sine theta, and we squared that, r dr theta. All right. Alright, so going through this, we multiplied the r through here. We went ahead and did the integral with respect to r, right? Plugged in the 2 and the 1, okay, and did the integral from 0 to pi d theta. And you end up getting 15 pi over 2. So again, you can go through this. This is in that section of 15.3, this particular problem. What all we really did was, instead of looking at the function, a Cartesian coordinate function, we mapped it to a polar coordinates. And then obviously we had to change the integrals from 1 to 2 and 0 to pi, making sure that we have r dr and then d theta. So what we have done so far can be extended to a more complicated region, so outside just the rectangular region, the polar rectangular region, and we want to look at the type 2 region here, where your x is a function of y, so we have h1 and h2, just like the type 1, type 2 regions in the rectangular that we did in 15.1 and 15.2. So here your r is between h1 and h2. And your theta is just going to be between alpha and beta here. All right, so again, you're taking that double integral around a general region D now, and here is your formula. So this is the formula we'll be using. So in particular, if we take the function f x y being just 1, and our h1 is 0, our h2 is some sort of function with parameter theta. In this formula, we see that the area of the region D bounded by theta being from a to or alpha to beta, and r is going to be that h theta. So we've got our double integral of 1 dA, h1 is 0, h2 is just your function, h theta. R, dr, d theta, we go ahead and integrate. And you see that this formula here is really, when you have something like this, is going to be, it agrees with that 10.4.3 formula that we had gone over. Right? So let's see that. We had talked about the that rose curve. So looking at that rose curve again and finding one of the curves, one of the petals. So let's see if I can actually draw that rose curve. It's a thing of beauty here. All right. So we know that theta is pi over 4. So between negative pi over 4 to pi over 4, we're just, again, just like the previous example, we were trying to find the area of the rose curve. And we used this formula, this area formula. So looking at the double integral, our region D, which is going to be defined by r theta. Again, theta is between pi over 4 and pi over negative pi over 4 or pi over 4. And r, you start at 0 and you go to cosine 2 theta. So one of those petals, right? So just finding the area there. That's our theta. We're going from 0, right? 0 to cosine pi. R dr d theta. And you're going to see, I can write this fast enough. We integrate and we get 1/2 r squared, right? From 0 to cosine 2 theta. So you see how, d theta obviously. Alright, so you see how that looks from the previous section. I think that's 10.4. Alright. We go ahead and we do that integration, and we're going to get pi over 8. So we can do the double integral and get an area here.